Fine. All right. How are we doing there? We got somebody else. Good morning. Um, I hope you guys are doing all right. I'm recording this so that I don't anticipate we'll be here too long. But while we just got the two of you, we can have an open mic. How's everything going there with you guys? All right. If you guys are good, it's probably early in the morning. Pretty good, no complaints. Thanks, Jess. I appreciate it. Um, I'm just going to continue on there with the week 6 stuff. Um, there's really not a lot going on as far as math goes, other than my marking, which I'm hoping to. Morning, Elena. Yeah, apologies there on the marking. It's if I had a stack of papers, like quizzes or assignments or whatever, I could just wing through them. But the everything I got to mark it one by one, and I got to wait for Blackboard to upload. So it's taking longer than I thought, but we'll get it done there. I'm hoping there in the next couple days. That's what I'm thinking. And but all seems all right. I hope the case studies are going good. I don't think it's too bad. The data is all there. You guys can have some fun with it. And good morning, Logan. And so that's where we're at right now. There's no emergencies as far as I can see. But if there is, let me know. And but other than that, we're just trucking along. And what do we got due after reading week? The case study is due the week 7. Okay, so we have you guys have lots of time. Then week 8 will be quiz 2. Week 9 will be test 2, and then we're into the downswing. So hopefully you guys are doing all right. It's early morning, but I hope you guys have the window open and enjoying a bit of fresh air. If there's no emergencies, I will shut up and get on with it. So, all right. So again, if you guys are doing, if there's any issues, just let me know, okay, and we'll get all this done. So, if y'all are good, I'm good. Let's get this going. And if you guys have any questions, my screen is kind of off to the side there, so I won't be able to read comments. But just give me a shout out. There's only 5 of us. All right. That's all right, though. It's early in the morning, and thank goodness I'm recording this. So, let's go. Today we're on to just a little bit further there of the mean, okay? And if you're just joining, don't worry. We haven't really done anything yet. You can see me after if you have any questions or interject anytime you want. It's a democratic classroom. So, let's go. Measures of central tendency again. We're kind of looking at the data in its totality now. And because you guys are experts at manipulating data, we're going to take that on. And now we're kind of looking at the data as a whole. We're getting there. Okay. So we're going to deal with the mean, 2 aspects of it there, the arithmetic mean and the non-arithmetic mean. Let's go. We've covered their mean, median, mode there last week. Today we're going to talk a little bit there about the mid-range. It's really easy. I think that's only 1 slide, and I'm kind of throwing that in so that it will play a part after reading week. Well, that's all part of my plan. So, and then today's focus is going to be on these 2 right here. Arithmetic mean and non-arithmetic mean. Okay, and are they difficult? No. Okay, are they a little different? Yeah, but they're not bad. Here we go. I think this is the only slide I have on the mid-range. It's pretty easy concept. You have your data. Okay, and what we're going to do is you're going to take your highest value and your lowest value, okay, and then you're going to add them all up and divide by 2. and this will give you your range. Okay, and what we're talking about here in this case here is your mid-range. All right, and it's another way of kind of quick, easy peasy finding the middle. All right. The mid-range is defined as the sum of the lowest and highest values in the data set and divide by 2. So in this case here, you got 2, 3, 6, 8, 4, 1. Well, your lowest number is 1. Your biggest number is 8. Add them up, 9 divided by 2 is 4.5. So that gives you kind of a middle value, which is just another way of expressing where the middle is. And we've seen that there. We've done mean, median, mode. Here's a mid-range. Here's another one there. This one here it'll factor in later, probably week 8 or 9, somewhere in there. Or sorry, week 7 or 8. So that's the mid-range. Crazy stuff. And this stuff here, again, I'm foreshadowing where we're going. Okay. So this stuff here really doesn't have anything to do with the arithmetic mean or the non-arithmetic mean, but I'm kind of multi-dimensionally teaching, okay? And this stuff here will become important as we get moving. Symmetry. And you remember we were talking about this is your population. Whatever you're measuring here, okay, the number of bananas eaten daily, you know what I mean, by people over 40, whatever. You want to see here that in a perfect world, you'll see here that the population, okay, and you know what I mean, this is people who eat 1 banana, and then 2 banana, and then 3 banana, and then 4 banana, and whoa, the average, the mean, in this case here, the mean, the median, or the mode, number is 5 bananas a day. All right? Again, it's nonsensical, right? But you can kind of see what I'm saying here, is that the majority, and you'll see here that, and we'll actually get into exact figures, but you'll see here that the majority of the data is in here. All right. So, and you'll see here that, let's say that the mean is 5 bananas a day. Well, it's perfectly split down the middle. And you've got 50% of the data on this side. You've got 50% of the data on this side. See how you've got a peak and it's exactly symmetrical. And this is... we'll get into the names there later, but here we're talking about the population of your sample as a whole. And in this case here, the mean, the median, and the mode are all going to be the same thing. Let's go. You can have other types of distribution. Like this one right here is the one we just saw, right? It's perfectly symmetrical, equidistance. The mean, median, mode is all the same. 50% of the data is over here. 50% of the data is over here. Perfect, perfect, perfect. But you can have different distributions. You'll remember the word there, outliers. Skewness, where there's something going on, like it's not an equidistance distribution here. And you'll see here in this one here, a positively skewed or right skewed. Okay, where you'll see here that there's something going on. You've got high numbers here and then it drops. Interesting. And then you have left skewed. Okay, something different is going on here. And these are all perfectly normal distributions. It's just trying to figure out how they all work. So just a bit of foreshadowing there, nothing too crazy. This is where we're at there today, these two here. Last week there we covered these guys here. Now we're on to the arithmetic mean and the non-arithmetic mean. Time for a coffee. My tongue isn't working. Time for a coffee. Okay, I'm going to get out of slideshow mode. All right, so here we go. Yeah, simple arithmetic mean is not always the best way to calculate the average of a set of data. In all examples below, the simple arithmetic mean would not provide a true average. Sorry I had to read that, but let's have a look here. Marks from 6 different evaluations, each weighted differently. Now, what do I mean by that? Well, you have a test that's worth 10%. You have an assignment that's worth 15%. You have an exam that's worth 25%. How do you calculate the mean from this? And this is something true and dear to your hearts, because in your Blackboard marks, you can go in there and you'll see a weighted column. I don't know if you'll see one there from my course yet, because I don't normally put it in until the last couple weeks, as marks start to accumulate, and you've got some meat on the bone there. But we're going to get into the weighted mean. Another example here: figure skating scores from 10 judges with extremely low and extremely high scores. So here you've got these outliers again, right? Like if all of your data is around here, right around 5 bananas, but then you've got this one person who eats 18 bananas a day, well, that's going to skew your data that way, right? So there's something going on there, but we'll get into all that. The contributions from each valuation score are not valued equally, therefore an arithmetic mean may still be calculated, but using modified formula. Okay. 5 consecutive annual rates of growth on an investment. So if I'm investing at 15% there the first year, which is crazy, that's great. And then the next year, I'm that same money is being invested at 18%, and then the next year 19%, and then 20%. And I want to calculate an average rate. How much am I making an average rate over that time period? We'll get into that. Rates of speed of a triathlete in each of the 3 different events. Well, first event you got swimming. Second event you got bike. Third event you got running, marathon. Okay, you're traveling at 3 different speeds, so how can you compare apples and oranges, kind of a thing, right? So we're going to get into all this there, the non-arithmetic mean. Okay, not too bad. So there we go. Just a little bit of recall here. We're going to go into like an official definition here. An outlier is a number that is very different from the rest of the group. Right? If all your data is in and around here, well, that tells you something, that all of these people are like-minded regarding this one attribute. Okay? And that's what if all of your data is here and you've got one person out here, it's interesting. There's 2 ways you could approach this. You could just snip that person eating 18 bananas and just look at these guys here, right? But then you could also look at the outlier as, what is this person doing? Are there any other people out there eating 18 bananas a day? Maybe not 18. Maybe in this village, everyone's eating 10 bananas a day. Who knows? I don't know. And outliers, they can be disregarded as not important for this particular study, because if I want to look at this group of data, that's what you're looking for, right? But outliers can be included as something important. And good morning, and if anyone just joined in, I hope you guys are doing well. You haven't really missed much at all. I am recording this. If you guys have any issues at all, let me know. You guys have been quiet on email, and you guys are a good class, and I hope everything is all right. And don't leave things there to the last second. If something's bothering you, then email me ASAP, because we have lots of time. Okay, and but I hope you guys are doing well. Any issues, just get a hold of me there. An outlier is a number that is very different from the rest as a group. If the data set includes outliers, these will strongly affect the value of the arithmetic mean, and it'll affect the shape because you've got that skewness right now. We want a nice perfect distribution like we saw there earlier, but if you have outliers there, it can pull it this way or pull it this way. May be helpful to remove the outliers from the data set. Why not? This is statistics. We can do what we want. Alternatively, it may be helpful to calculate the mean twice. Once with the outliers included, and again with the outliers removed, and compare. How badly is that outlier going to skew your data? That's the nice thing about statistics, is that you can kind of fit the answer to suit your needs, because this is your study. Maybe you guys go on, please go on, and after you guys get your nursing, your paramedic, your firefighter, your vet tech, go on, get a Bachelor of Science, go on, get a master's, go on and conduct some studies there into animal welfare and wildlife conservation. Do some studies. It's a lot of fun. It really is. And hopefully this course will set you on the road to it. And let's go. Showing the effects of extreme outliers. And you have a look here. It's a very simple example. Here I got 3, 40, 45, 52, 60, 66, and 70. Well, you just look at this data and, what do I got? 7 data points. 6 of them are, double digits, and they're not 10, 11, 12. They're starting at 40 and going to 70. And then all of a sudden I've got this 3 in here. But anyway, easy peasy. Let's calculate the mean of this sample. There's x bars equal to sum of x divided by n. And you add them all up, 336 divided by 7 is 48. So that's my mean for this data set. But what happens if I remove that 3? And then there are those 6 numbers there, 40, 45, 52, 60, 66, and you divide it by 6, you get 55.8. Let's go back again. So all the data, the mean is 48. But if I remove that 3, which is that outlier, it's not even close. And you see here, 40, 45, 52, 60, 66, 70. These numbers kind of go together, right? There's that data that, all the, there's your population, and it's kind of all telling you a story. But then you have this 3 over here, right? But we remove that and look at our average now, 55.5. And recall that the mean for all 7 values was 48. So you can remove one of those data points if it doesn't suit your needs. Okay. You can also do what's called a trimmed mean, and usually we do a 10%. Where I'll get you is on a 10% mean. Let's keep it easy peasy, shall we? I gotta get a new mouse. Keeps on, I click once and it double clicks. So a trim mean is a simple arithmetic mean of the middle values in a data set after a certain percent, 10% of the data. And what we're talking about here is you're going to take 10% of the highest, 10% of the lowest. We'll show you this right here. It is used in cases where it is important and outliers never affect the outcome. Let's have a look. There are 4 steps. So here we've got a competitor and a judge in a judge sport is given the following 10 marks out of 10. So this figure skater or whatever it is, Olympic diver, 8.6, 8.2, 7.8, 8.4, 9.0, 6.8, 8.2, 8.6, 8.0, 8.6. So determine the competitor's final score by calculating a 10% trimmed mean. All right. So arrange the data from lowest to highest. And we've done that, 6.8 to 9. Okay. There are 10 numbers in here. Okay. Identify the number of data points to be removed by multiplying the size of the data set by the percent to be trimmed. Okay, so the percent is to be trimmed is 10%. Therefore, since there are 10 data points, 10% of the data is represented by 1 data point. So if we do a 10% trimmed mean, okay, you got 10 data points. Well, 10% of 10 will be 1 data point. Okay, what do we do with this now? Remove the number of data points from the top and the bottom. So you see what we're doing here, a 10% trimmed mean, okay, we're going to take the bottom 10% and the top 10% off. So now we're just going to deal with these guys here. That's all it is. All right, nothing too crazy. And then what are you going to do with those numbers left over? You see there? You're going to do this exact same thing. We got x bar is equal to sum of x divided by n. Now you just have those ones there because you've snipped off the top and the bottom 10%. Now you only have 8 numbers. Add them all up, divide by 8, and there we go. The competitor's final score based on a 10% trim mean, 8.3. Not too bad. The weighted mean. Now this is where classic example, quizzes, labs, assignments, exams, they're all weighted differently. How do we calculate our average using this method? Well, this formula here, there's your x bar, okay? The sum of all weighted data values divided by the sum of all the weights. So this is your formula here. Now, how do we do this? It's easy peasy. It's not too bad. Okay. The weighted mean is similar to an arithmetic mean, arithmetic average, but instead of all terms contributing equally to the final average, some terms contribute more than others. And if you look at this simple little example here, we're dealing with a furniture store is selling some dressers, and here we have the less expensive version made of particle board, press board, and that's going for $100. You have aspen wood, woo, and it's selling for $200. What a great color. And then we have oak, all right, which is $300. So this one here is selling for $100. This one here is selling for $200. This one here is selling for $300. Okay. So if we just do an easy peasy average, the average price of a dresser in this shop, well, you got $100 and $200 and $300 divided by 3. So the average price per se is $200. So the aspen is the, it represents the average price, right? Well, let's kick it up a notch here. On average, over a 2-week period, the store sells 6 particle board dressers, 4 aspen dressers, and 2 oak dressers. So this is an average on a 2-week basis, right? So 6 of these guys are sold, 4 of these guys are sold, and 2 of these guys are sold. Okay. Now, what do we do? Well, this may seem complicated, but please don't let it. You'll remember this one right here, right? Okay. Which isn't the right answer, but what we'll do is here is you'll see, and I left this wrong here, and I want to show you what's going on, and it's 166.67, and you'll see here, now, you take the weight times what it is. And so you see here, you've got your 100, your 200, and your 300. Well, how many of those did you sell? Well, I've got 6 of them. So 6 times 100 plus 4 times 200 plus 2 times 300. And this is your weight value. And in this case here, it's how many you're selling over a 2-week period, right? So, and you'll see here that 6 times 100 plus 4 times 200 plus 2 times 300, which is, it's written 3 different ways here, okay? However you want to deal with it. And you've got 12 items because 6 of these were sold, 4 of these, and 2 of these. So that's 12 right there. divided by 12, and you get an average number of $166.66. And if you look at that, I really want, because, I don't want you guys to, to blindly just input numbers into a formula and whatever comes out, comes out. I've seen it so many times before where the calculator, even like when I was teaching calculus, some of the questions there were a page and a half to 2 pages long. One question, massive, massive questions. And I've seen students methodically, it's good, it's good, it's good. Oh, yeah. It looks all the way good. And then the very last step was a calculator error. I know it. I've seen it 1,000 times, 100 times. Okay. And want you guys, when you guys get a number coming out of your calculator, does it make sense? And if you look, I've sold 6 of the cheaper dresser. I sold 4 of these guys and 2 of these guys. So you can see how it's going to be skewed. If you look at our original mean there that we did, right here, the one that doesn't mean anything, okay? It's saying there that the average is for this one here, but here we're talking about the number of them sold. Well, which one did you sell more of? Sold more of these. So it's going to be skewed towards the cheaper particle board. Okay, and in that case there, you'll see that it's not $200, but in this case here, the weighted mean for the number of dressers sold is $166. It's pulled down below that $200 mean that we calculated there before. Why is it pulled down below? Because the particle board, the cheapest, there was 6 of them sold. Okay, so that's going to pull the mean down a bit. All right. Any questions with that, just let me know. But this is what you're looking there. The weight times the number plus the weight times the number plus the weight times the number there. That's how this one's go. And where did that where did that go? Right here. That's what I was looking for. The weight times the number. Okay, that's what we're looking for there. So, and just a kind of a summary, which I just kind of did already, but we'll summarize again. There's your average price of the dresser, which was $200, and you'll see there that the weighted average price of a dresser was $166.67. This number here, it's considered the weight of each unit, which in this case is the popularity, right? The number of units sold. Notice that in this case there, the weighted mean is lower. The weighted mean is closer to the price of the particle board dresser as more of these were sold. Okay, not too bad. What do we got here there? The average price of a dresser. Yeah. This is how we're doing this here. The weight times the number plus the weight times the number plus the weight times the number. Now, this is more in line to where we're going, okay? This one here, you want to know. Oh, did I just say that? Yeah, you really want to know this one, okay? Because this one here is something that you can take in your bag of tricks and carry with you throughout your life, okay? It's pretty simple, finding the mean based on different valued tests or in different valued categories. So have a look here. The final average in a subject is determined by 3 tests and a final examination. So I got 4 bananas there. I got 3 tests and a final examination. Each test is worth 15%. So 15, 30, and 45, right? And the final test is worth 55. So 45% and 55 is 100. So all of our numbers, everything is good to go, all right? And the student receives 65%, 75%, and 80% in the 3 tests and 90% on the final exam. The student did very well. So calculate the student's final marks with this subject based on the weighted mean. So there's your answer. Let's show you how we did it. And same question here, 65, 75, and 80%. Those are the marks received, but those tests were only worth 15%. Okay? So, what we're doing here. Sum of all the weights. So we got 15 times 65. Now you'll notice there, and I'll go into this a little bit, but you have to be able, for this course and for many of the other lectures coming, being able to change percentage into decimal, very, very importante. Okay, 65% out of 100%, okay, can be written as 0.65 divided by 1. Sometimes we'll use 100% is equal to 1, 65% is equal to a decimal, 0.65. So you got 15 times 0.65 plus 15 times 0.75 plus 15 times 0.8. So that takes care of the 3 tests. Okay, those are all 15% times their percentages, and then plus 55 times 90%. Okay, add them all up, you got 182.5%. That's how this one goes. Okay, if there's any issues with that, just let me know. Okay, it's the same formula as this one right here. There's your weighted mean. That's everything you want to know is right there. Okay. Now we're going to move on to the I think that's the yes, it's the non-arithmetic mean here. Okay, and there are, so just to recap, the arithmetic mean, we did the simple, the trimmed, and the weighted. So there's 3 examples there. Okay, we covered those. The non-arithmetic mean, there's one of them there called the geometric. Now, geometric means that things are expanding at a rapid pace, or things are, what's the opposite of expanding? Decreasing. There we go. At an expanding rate. So here we can talk about bacterial cultures. Here we can, well, I'll show you all these guys here. And there's also something called the harmonic mean. Are these difficult? Nah, not too bad. The geometric mean is, you'll see what we're talking about here. The geometric mean allows for the calculation of average rate of growth over a period of time. So rates of growth are multiplicative rather than additive. They grow exponentially. Like just the whole, there's the riddle there that I was told as a joke when I was a kid. Would you rather take $1 million now, or 1 penny doubled every day for a month? And you know what I mean, at first glance, sure, man, I'll take the $1 million. Yeah, see ya, I'm out of here. But if you take a penny doubled every day, 1 penny day 1, 2 pennies day 2, 4 pennies day 3, 8 pennies day 4, 16 pennies day 5, 32 pennies day 6, and it actually, don't quote me on this, but you can figure it out there that it's a lot more than $1 million after 1 month. And that's the whole idea of what geometric growth means. It starts off slow and then wham, takes right off. So this is what I mean there. The rates of growth are multiplicative rather than additive. So the arithmetic mean is not really a good way to do this, utilize this. The geometric mean, used to measure in accounting and finance for processes involving compound interest, making your money grow, right? Bacterial cultures, exponential decay. You guys have covered there. You should be covering. You should have done there a little bit there last semester on radioactive isotopes, carbon dating. Any issues with that? Just there, let me know. So a little bit of a math recall. If you see a fractional exponent, like let's say here I've got a to the power 1/5. Well, really that just means the 5th root of a. So, and to give you guys an example, now this is part of the problem of not having you guys in class, because normally what I would do is I would show this slide and I would stop teaching for like 5 minutes and to let y'all get your scientific calculators out and try this. Try inputting this into your calculator and see if you can get the answer 4. Now, you may have to use the square root button. It should look like an X to the square root. If you have any issues with that, please let me know, because you can't do the quiz, you can't do anything coming up there after reading week unless you can do this. And you figured every calculator is different, all right? And if you can't get this answer, okay, so here we have 16,384 all to the power of 1/7, which just means the 7th root of this, which is 4. Okay, so 4 times 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 4 is this number here. So that's what we're talking about there. Any issues with that, let me know. This should be the function on your calculator. I've kind of tried to do it as best I could. That's what I use on my scientific calculator. It's a pain in the butt to get to. I have to go to Shift and hit these buttons here, but try it out. If you can't get this answer, email me. We'll set up a WebEx and we'll do it all and we'll get you guys going, okay? And I kind of already alluded to this there, percentages and interest. Remember that 100% is equal to 1. Another example here, 145% is equal to 1.45. Another example here, 67% is equal to 0.67. Okay, you got to be able to flip in and out of decimals to percentages. Okay, so if you have a look here, I just wanted to show you guys this. I don't know if you guys have done this. It's really not a difficult. I'm just throwing this at you so that some of it'll stick, and then in about 2 or 3 slides there, we'll go over it in more detail. But if, let's say, you invested $100 for 3 years at 17% interest, okay, how do you calculate this? And, well, you've got your $100, okay. Now, you invest money, so you put in your $100. Hopefully, you're not going to get less than your money back, right? You want to get your money back plus. So there's your you put in 100% of your money. Well, now you want to get more money back because you're putting your money in the bank and you're putting in the time. So you want to get more. It's called investing, right? So you've got your $100 times 1 plus 0.17. Now, what this represents is basically 117%, right? That's what, your investment rate is 17%. So yearly, you should expect to get back. The first year, you have $100 plus $17. So after the first year, you should have $117, right? Well, then now, going into the second year, you've got $117. Now you're going to make 17% on that. And then going into the third year, you've got more money, and you're going to invest that at 17%. Holy, can't believe he's going over this at 8 o'clock in the morning. I hear you. And how we do this here is just the skinny of it all is there's your initial investment, okay? This just means 117%. That's how much money, the percentage you're expected to get back. And then there's your 3 years, right? And you could calculate this out, which is 100 times this, times this, times this, and you'll get a number. And I think it works out to be like 160, 170 bucks, somewhere in there. Okay, so we'll get into that there in a little bit. Okay. To recap again, the geometric mean allows for the calculation of the average rate of growth over a period of time. So you'll see here, don't really want you to focus too much on this formula here, but I will explain it. So this is your geometric mean, okay, which is the average rate of growth over a period of time, right? And you've got pi here, which is used to represent the product, whatever you're talking about, all right? You've got the value of the term, and you've got n is the total number of terms in the data set. And you see there's your fraction, right? Which you can flip and make into a square root. All right? So if you have 1 over n, it's going to be n square root whatever's inside here. So let's have a look. So in other words, the geometric mean satisfies the following formula. What they've done here is they've just flipped this formula around and they've written it like this. Whoopie-doo. Whatever floats your boat. Okay? However you want to do it, whatever's easiest there for you. But really, this is what we're doing here. Okay? So the geometric mean, the geometric average here, you have whatever your data points are, all to the power of 1 over n. You could also write it as n square root. So let's have a look here. The geometric mean of these guys here. I got 4, 8, 9, 12, and 15. Now this is pretty nonsensical. The geometric mean, so we're trying to find the average rate of growth over a period of time. Well, we didn't really give you a real time period. We didn't really give you anything. So I don't really want you to take too much meaning from this other than structurally being able to do the mathematics. Okay, so the geometric mean here, I got 4, 8, 9, 12, 15. Well, plug them all in, okay, and then all to the power of 1 over 5 because there are 5 data points. And if you can calculate this, that's awesome. If you can't, try it a couple times because I want you guys to get this answer. However you do it, you can even use the the little hat button, your exponent. I was trying it there last night, just different ways there. You could actually put in a bracket. They use the little triangle, the little hat, and then bracket 1/5 bracket. It even works that way. So there's a number of ways that you can do it. I don't care how you do it, as long as you do it and you get the right answer. That's what I'm interested in. So if you can't do it, shoot me an email. We'll set up a 2-minute WebEx. You can show me your calculator there, and we'll just kind of old school it and get it all done. Okay. So the geometric mean for this data set here is 8.77. Now, what does that mean? I don't really care what it means right now because it's nonsensical. But if you guys can do this, the whole point of this slide is being able to take a data set and calculate its geometric mean. We'll get into more what exactly it should be there right now. Now, this is the question here I want you guys to have a look at, all right? Because you will see this again. So Sam invested $100 for 4 years, all right? So if the growth rate for each year, so the first year was he was making, he or she, they were making 10% on that $100. Second year, they were making 14%. The third year, they were making 17%. And then the last year, the fourth year, they were making 18%. And then the question is what is the average annual growth rate over those 4 years? So, the money was being made at all different rates, right? But if we look at the 4 years as a snapshot, what's our average rate of growth there for the 4 years? And you can see here that, you could add up all the percentages, divide by 4. You could just say that the average growth rate was 14.75%. No, can't do it. Okay. What we got to do, it's a little bit more complicated, but I'm going to break it down. It shouldn't be that bad. So the same question right here. Okay, blah, blah, blah. Okay, 10%, 14, 17, and 18. Now, what we're looking here to do is I want to just break this down here. At the end of the first year, okay, there's your $100 and 110%, right? That's what we invested it at. So at the end of the first year, made 110 bucks. All right, which is this number right here. And then for the second year, which is at 14%, we multiply by 114%, which is 1.14. And you see, made 125 bucks. See, the first year, Sam only made $10. The second year, Sam made $15. Actually made more. Because Sam had more principal. Sam had $110 as opposed to $100 the first year. And also, the interest rate is at 14%, not 10%. So they're making more money. At the end of the third year, you'll see here that right there, that encompasses the first 2 years. And now the third year, which is at 1.17%, and you'll see there that that's the money that was made there. Okay, so Sam actually made around $21 there, year 3. And the end of the fourth year, and there's the first 3, there's the fourth year, and you'll see there that $1.73, and you'll see there that Sam actually made around $28 there the last year. And you'll see how this geometric growth goes. And eventually, it starts off slow, but then just takes right off. Okay? So how we're doing this here is all based on the original slide there from, where did I show you? The Math Recall. Right? This one right here. Okay? And what we got here is, in order to calculate the average annual growth rate, we need this little formula right here. And you'll see here that this is your principal. That's how much money you invested. Okay? And then the 1 plus the interest, right? That would be 110% or 114% or 117% or 118%, whatever the percentage is. Okay? And you'll see here that how many years? 4 years. And how do we break this down? What does this really mean? Well, there's your 100 times your first year at 10%, times the second year, which was at 14%, times the third year, which is at 17%, and then the fourth year at 18%. And I've just broken this down here, and you'll see right here, the exact same banana. Okay, so there's your 10%, there's your 14, 17, and 18, and add them up, right? So you got 1 plus, you got this right here, and you'll see that I've got an equation. And what I did was, you have 100 on this side and 100 on this side. We'll just cancel them, all right, because we can do that mathematically. And so then all you're left with here, because I've taken this 100 away and this 100 away, because don't need them on both sides, because I'm looking for G. That's ultimately what we're doing here. And so now you've got 1 plus G to the 4th times these guys over here. Okay, so you would multiply all these together. Take your 4th root of this side, 4th root of this side, and you get G is equal to this whole thing here turns into 1.14703773. You bring this 1 over here, minus 1, and you get this average growth rate. Okay? And try this out a couple times. It's not too bad. It looks kind of wordy and all this, but it's not. You just follow this step right here. You can't really go wrong. It's just a matter of plugging and playing. So you will see a percentage question like this again, promise. You'll see it all over the place. Okay, it's not like I have a lot of question types to go after you. It's not like bio or chem where there's 100 million types of questions. You know what I mean? So this is the slide that you're looking for if you're dealing with an average annual growth rate. Here's your how much you deposited, and then your percentage is all in here, a number of years. Okay, and then just break it down, year 1, year 2, year 3, year 4, plug in your numbers, play, away you go. So therefore the average annual growth rate over the 4 years was 14.71, percentage. That's that one. Okay. The last part of our lecture here is the harmonic mean, which is the most direct method to calculate the average rates of change. And a good example here is the rates of speed. Okay, the rate of change of distance over time. And if you have a look at this example here, a runner runs for an hour at a constant speed of 15 clicks an hour. So it's running in this direction there for 1 hour, 15 kilometers an hour. And then turns around and walks home at a constant speed of 5 kilometers an hour. What is the runner's average rate of speed? Okay. There's a couple ways here we're going to do it. You guys can choose the easiest way that you like. Okay. So intuitively here, we want to say the answer is 10 kilometers an hour, right? 15 divided by 15 and 5 divided by 2, 20 divided by 2 is 10. We can't do that. So because the runner is running at it for an hour, 1 hour, 15 kilometers. So in 1 hour, they ran 15 kilometers. So they're 15 kilometers from home. And then the runner walks back 15 kilometers back home, this time going 5 kilometers an hour. So logically, it took them 3 hours to get home, right? We'll get more into this here. So again, you're kind of dealing with you're dealing with apples and oranges here. And you're dealing with running 15 kilometers an hour and then walking at 5 kilometers an hour. How do you compare these? So if the runner runs for an hour at 15 kilometers, they've run a total distance of 15 kilometers from the house. At a return rate of 5 kilometers, okay, it'll take 3 hours to walk home because the runner ran 15 kilometers an hour in 1 hour, that's 15 kilometers. So the person has to move back 15 kilometers to get back home. Well, if you're walking at 5 kilometers an hour, it's going to take you 3 hours to walk home. All right. So thus he has traveled a total of 30 kilometers over the course of 4 hours, making his overall speed 30 kilometers divided by 4 hours is 7.5 kilometers per hour. You look at your total distance divided by your total time, 7.5 kilometers an hour. Easy peasy, not too bad. This example differs from previous examples in that while the distance at both speeds is constant, the time is not, and it is the time spent at each speed that determines the average. So in this scenario there, the runner ran at 15 kilometers for 1 hour, but walked at 5 kilometers for 3 hours. As such, if we had used a weighted average, assigning a weight of 1 to the 15, and then 3 hours to the 5 kilometers, you would still get the same answer. 1 times 15 is 15. 3 times 5 is 15. 15 and 15 is 30. Divided by 4 hours is still 7.5. So you can see here that, you know what I mean, just kind of deducing this mathematically, you get 7.5 hours. If you want to use the weighted mean, you're still going to get 7.5 hours. The harmonic mean, which you don't really have to know, but I'm going to show it to you anyway, because any of these questions here that require the harmonic mean, you can just use this or this style here. So have a look here. The PowerPoint's saying here, however, there's a more direct method to calculate this kind of average known as the harmonic mean. The harmonic mean takes the reciprocal average of the reciprocal values. And you'll see this formula right here. And you know, we'll go through it and we'll have a look here. So here's your harmonic mean. Here you have the number of total terms in the data set. Okay, and here we have the sum of the reciprocal values. So reciprocal means you're putting it over 1. So the reciprocal of 2 is 1/2. You have the number 2. Okay, the reciprocal is 1/2, which is a half, right? So that's what I mean by the term there, reciprocal. Let's have a look here. Same question, and you just plug and play. So you have your number at exactly the same question, 15 kilometers for 1 hour, and then back home 3 hours at 5 kilometers an hour. So your number of data points is 2, and the sum 1/15 plus 1/5, 15 kilometers an hour, 5 kilometers an hour, which is equal to 4/15. You do the heavy duty mathematics, and you still get 7.5 kilometers per hour. Okay, so on a testing situation, you could use a harmonic mean, but then you really don't have to. You could use your weighted mean, or just kind of logically deducing it all by yourself. So that's what we're going on there. That's your harmonic mean. I've got these ones here. Determine the best type of mean to use to solve for the true average in the following case. So like these tests here, they're open book 100%. So the questions there that I give you are the questions there that you've had there before. So on a testing situation, you know what I mean, you have all of your stuff ready and available to go, and you have a look here. The following data indicates the money spent in dollars on books during 2015 by 10 college students. So you have a look here. I got 900, 750, all these. I got all these numbers here. What do you see? Is there anything there that could cause an issue? And you'll see here that these the money spent in dollars here, 900, 750, 601, 945. This person only spent $85. Nice. All right. What do we do? Probably do a 10% trim mean. And you would go through that. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what's going to happen is you're going to knock off your lowest one. And which one's your highest one? This one right here. So the highest 10%, lowest 10% gets the snip, and therefore you calculate your mean from that. On a trip, Sarah drives at 80 kilometers an hour for the first half of the journey and 100 kilometers an hour for the second half of the journey. What's her average speed? You could use the harmonic mean. You could use the weighted average there. Have some fun with that. That's what's going on there. Also, I noticed, I haven't heard from, but I just wanted to let you guys know that the questions at the back of the chapter, very important. I'm not sure if all of you guys have the book or not, because every week there, you'll notice, I give you the answers. Okay? Like these are all the answers there to all the questions, but these answers don't have the questions in them. So if you don't have the textbook, these answers are meaningless. Well, I don't know. I hope I don't get into trouble here, but I want you guys to try these out. So what I've done here is you guys have the questions from the textbook, okay? And I want you guys to try these out. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16. Well, you've got them all. You've got all the answers here, okay? And okay. However you guys do the harmonic mean, do it. Have some fun with it. There's your calculating on percentage, first year, second year. Try some of these out. Have some fun. That's what we're doing, and I am done. So, you guys have any questions? Nah. Get out of here and enjoy your day. If I don't talk to you guys, have a great, awesome, exciting reading week. get out and get some vitamin D, some sunshine, and oh, you guys are good, man. I tell you, you guys are top drawer. Please keep me in the loop. If you're having any issues, let me know. Don't let anything slide. Email me, bother me, hassle me, irritate me. I love it. I love it. All right. So you guys get out of here. Enjoy your day. I'll post this there to YouTube. Be well, guys. Take it easy, and we'll see you soon. Bye, guys. Now.